Okay, so quickly let's start. Oh no. So for the operating point analysis, so we'll start with this. You scroll down to this point. Okay, there's nothing to do here. Okay, don't worry, just okay. So what to do now is go insert, hit the insert button, then go to the scheme library. So if you're there, look for ngspice. Oh sorry, let me open this. Look for ngspice value, get value, something like that. So I think this ngspice get value symbol. So ngspice get value symbol. So okay, I'm just going to place it here. So let me zoom in so you can see. So let's just focus for now. Let's just focus on the amplifier. So I'm placing, look at it, that's this symbol, I'm placing it here. So I'll just make a copy of this copy. I place it here, copy, place it here, copy, place it here. I think so. We just want to get operating point of four parameters. So there are many more, you can get so many, but let's just go with 4 because it means 4 for each of them. So for one of them, so I want to get, so I come here, I want to get the one of the parameters, operating point values. I want it's for the current of transistor 1, so ID1. I'm labeling it as ID1. Then the node, so I'm calling it's a current, right? So I'll call it I into brackets. Then this is how to get the, like in Spice, if you want to access a device, this is how to access a device. If you want to access, let's say, a property of a device, so this is how to access. So you say m so sorry, you say at, you use the at m dot, so what's the name of the device? The name xm1, so xm1 dot m naught. So what's the parameter I want to access? What about the device I want to access? So it's the current ID, the drain current. Then close the brackets. So okay, the next thing, you can see the value is already updated here, but let's just not worry. Another value I want to get, so it's still for, I'm still doing for transistor 1. So the another value is the transconductance gm1. So I'm going to equal to gm1. It's neither a current or voltage, right? So I'm not starting with I brackets. I'm not starting with I bracket. No, I'm not going to start with that. What I'm going to do is, since it's neither a current nor voltage, I'll just go ahead and access the device and get the value I want to get. So again, at m dot, so still xm1 transistor 1 dot m naught. So what am I getting? gm, close, and that's all. Yeah, so that's all. Another value I would like to get is the let's get the VDSAT. Yeah, the VDSAT and the VDS. So VDSAT, or let's just get VDS first. So VDS, that's the voltage, the drain to source voltage. So that's a voltage, right? So I'll start with voltage brackets at m naught, at m dot xm is still transistor 1, m naught yeah, brackets, then VDS, VDS. So then close the other bracket. So yeah, that's it. So for the last, I'm tired of typing, so how I'm just going to do, I'll just delete this, make a copy of this, because the next one I want to get, let's get for the, so the next one to get for this VD sats. So I just need to do is just come here, sats, it's still M1. Yes, then okay, I would like to get one more. Let's get for the threshold. Let's see how things are working. So threshold, so VTH, so that's for M1. So I want to get all these parameters, all these operating points parameters for the rest of the transistor. So all I just need to do is I'm just going to copy everything, copy, I'll bring it here, copy this GM, bring it here, copy this VDSAT or VDS, I bring it here, copy the VDSAT, bring it here, copy the copy the threshold voltage, I bring it here. Okay, copy. Then all I just need to do, I'll just open up, then change everything. Since it's anyway I'm seeing M1 or like XM1, I'll change it to 2. So 2, I'm changing it for 2. So GM 2. So since I'm just going to repeat the same thing, let me just pause and complete it. Okay, so welcome back. I've completed everything. Now you have for M1, M2, M3. So I'm just going to zoom out or just zoom full. So I zoom full, then I do Ctrl S to save my work. So I think I'm ready to do I'm now ready to do the analysis. So to do that, I'm going to hit the netlist button. So the netlist button, I get to see my netlist. For your case, it may not be showing depending on which. So from here you can see everything. It seems to be okay, nothing wrong with the netlist. I'll just save and go. If your netlist is not showing, just come to simulation and tick this show netlist after netlist command. Then next I hit the simulation button. So everything seems to be working well, no error for simulation, and yeah, okay. Then next I hit the wave button. So for the first, I want to do operating point analysis, right? But then I want to see the annotations, so I'll click on this up of the annotation, annotate. So then yeah, then I click open. So let's zoom in to let's just zoom in to see all the updated parameters. So this is what we have for the updated parameters. So it's yeah, we can see this result is telling us that the current through M1, it's about 103 microampere. So you can see, then, which is pretty close to what we wanted, right? We wanted just 100 microampere. So Spice is somehow agreeing to our calculation. Then for our GM, I think this is about 788.3 microampere. Then but from our calculation, if you remember, where is it, we got the transconductance to for each of them to be about 800. That's that's pretty close. That's a good agreement between our hand calculation and spice results. Then okay, we did not calculate all of this, but we don't calculate VDS, but we can try that. We can calculate that later, but we calculated VDSAT, so which was 0.25, right? And this 0.217, again, I mean, this is pretty close. You remember I used threshold voltage of 0.65, again, pretty good. Let's go for M2. Of course, the current flowing through M1 should be the same thing as current flowing through M2, so you have it here. Again, GM, wow, unlike M1, the GM got to up to 800 for M2. VDSAT about 0.2, also we calculated for 0.25. By the way, the VT, the threshold for these two guys are not showing because I did not do something to the spice net list here. I'm supposed to add it, but I did not, so that's why it's not showing. So but we can just leave that. Then coming to M3, we get the current M3 is exactly 100 micrometer, but I mean, why not? I mean, M3 is directly in series with this 100 microampere of current source, so there'll be a problem if it wasn't. So this makes sense. This is what we want perfectly for these two guys, but it's fine. Spice and calculation do not need to exactly agree for us to say if our design would work well. They just need to be in close range. And for GM3, it's 787. So these are pretty close values and pretty close. So you can see operating point is telling us we are good. So for your design to work well, everything needs to work well. You need to do the operating point analysis, you need to verify, you need to go ahead and check the transient, go ahead and check the AC. So for now, operating point is telling us that, and actually everything plays together. Operating points can affect the values you get for your transient, can affect the values you get for your AC analysis and all. So operating point is pretty close to what we calculated. So then maybe there's nothing to debug here, nothing to want to rearrange here, except maybe, of course, we can always come to tweak one or two things to see if these values will get closer. But for now, let's just quickly move to let's say the AC analysis. So if you want to do the AC, just hit the button, wave, come back to wave again, it's AC, right? So AC, then open. So so the next thing you do, it's double click. So I want to use this graph. Remember I added two graphs too, but I want to use this one up here. So sorry. So I just come to this graph I want to use. I'll double click, then this window will pop up. Then I want to plot the output voltage. For AC is like the frequency response, so I'm going to click on this. This is what I want to plot, V out, right? So click add. I just don't want to plot V out. I want to plot, AC, this thing usually in, it's in semi-log form, right, in dB. So I'm just going to do this V out, comment, then dB 20 brackets, the close. So this is the syntax. Then I'll choose the X, is it the X? Yeah, I'll choose the X axis to be log form, so log form X. So and we are okay, then it's okay. Then I can zoom full by coming just on the graph, then it's F. Okay, it's still not looking well that much. I can come to the Y axis here, place the cursor there and hit F button. it's still not zooming in full. There's issue somewhere. Let's zoom the horizontal. Okay, so apparently I think so for AC is not agreeing. It's not giving us the line. This is supposed to be the wave, but it's fixed on this. So so AC is not agreeing. AC is telling us there is issue, so we need to check something to get our gain value, because this will be the gain here. Yeah, you get. Oh wait, oh no, yeah, I missed something out. So what's the thing? You want to do AC analysis? Sorry, you'd have to edit this voltage source, this input voltage source. So you have to, what do you need to do? I'm going to add, see what I'm adding, 1 0 space 0, then quotation mark, everything in quotation. So I think with this everything should work fine. Sorry for that. So Control S, save again, start all over again, hit the netlist button, then after the netlist, simulate button, then not everything seems to be good, then hit the wave button again. Now let's do the AC. So AC, so open, let's see what it has for us now. I hope things should be well. So I come here again, come to this and F. If it's not working here, you come to the Y axis, F, and yes, we have it. Good. Wow, so nice. So let's see our DC gain. So I'm just going to place my cursor here and press the A button on the keyboard. So the value here is 25.36. So we're having 25.36 here. So that's 25.36 dB, right? So 25.36 dB in normal volts per volt gain, that will be 25.36. You do the conversion, your decibel to normal volt per volt, so that will be divided by 20. Then that answer you get raised to the power of then what you get, you raise 10 to the power of what you get, and it says 18.5 on my end here. So 18.5. And going back to our calculation, what did we get? What did our calculation predict? Wow, pretty good. 16. Our gain predicted, our calculation predicted 16 volt per volt. This gain depends on this channel length modulation parameters, depending on what you choose, depending on the very transistor model. So it just ranges from here to here. So again, that's pretty good, a good gain. For gain is either we have above or just what we want. So we never specify for gain, so that's really a good thing. Our calculation predicted 16, I got 18. Depending on this value, I think maybe why it got up to 18, maybe the spice wasn't using 0.24, used something less than that. I think it may be 0.22. if you try it, 1 over 0.25 times 0.22. Yeah, I think that's why. So you see it's still in that range, 0.22 to 0.38. So again, we're all good. Operating points smiled at us. Also now AC is smiling at us. So lastly, let's just confirm our transient. Transient, what do you have for us? Let's see if transient analysis is going to agree with us also. So again, you don't really need to start over again, since you've not changed anything there. Just come here and choose transient. So again, and you can come and use this graph if you want. I double click V out and V out, add. You can still use the first graph if you want, but just anyone. Then so again, zoom and zoom, So we can't see, it's supposed to be a sine, right? But it's just all looking straight. So let's check the, oh yeah, another mistake. I have not provided a sine input. Just like for the AC, I did not provide AC input, so sorry about that. So let's go provide a sine input. So sine, you can just remember this 0.9 is the bias. It must be there. It's constant. It's the DC. So this is how sine. This is syntax for sine. So you have sine open bracket. I think the first value, it's usually the DC value 0.9. The next is the amplitude, how the small signal, the sine wave, what should be the amplitude? Remember, this should be a small signal, so I'm going to choose just 1 millivolts. So 1 milli. I think the rest of the thing there is, I think I forgot in delay or something, so I'm just going to be adding 0 0 0. I think they're about, the sine takes about, is it 6 or 5 arguments? So I know this last argument here, so you can check the ngSpice manual for this. I know this last argument is usually the phase. I don't want it to be out of phase, so I just want it to be the normal sine, so that starts from 0, so the phase is just 0. So let me confirm, if let me check other past work, what's the sine. Oh yeah, I missed one, so it's about 6, right? Yeah, so the third argument should be the frequency of the sine. So let's come back here. So the frequency, so the third argument should be, so I'm choosing 10 kilohertz. So since I have the DC value inside here already, sine takes DC, so I can just erase this outer DC. It's still here, but had it been this DC, I use 0, then that's when I'll put the DC here, 0.9. anyone would work, anyone. So maybe we can just use this one. We're good to go. Since I've changed something in the main interface, so I need to recompile, like save, come back again, generate the netlist, hit the simulate button and move to wave. But now I don't need to repeat all those other analysis I did. I'll just go straight to transient. So from transient, yeah, so open. So I can go use any graph I want. I can use this one down, but I just want to use this one here. So F, zoom in the horizontal or the vertical axis. So zoom in. Let me give a better view so you can see. You already have a sine. Let me add the input. So let's see how the input and the output are varying. So let me add in, add, and let's see, let me change the color for the input. Let's say red. Let me zoom full. Okay, that's the problem. The input is too small. So what I'm going to do is I would just remove the input. I'll remove the input, then I would add another wave for the input. So simulate graph, add it from graph. So I'll double click, so just add input, so this will just be for the input alone. So add, okay, so you have the input. So zoom full. Where's the input gone? So let me zoom. Okay, so now since it's actually very small, so that's why. So now let's do something. So you can see the relation between the input and the output. So you can see the input wave when it peaked and when it's now down. You can see something. You notice something when this is going up, this is coming down. So remember, that's why they said the gain of a common source amplifier is what? Minus GM arrow O, right? So the minus is just the phase. They are like the input and the output, they are out of phase, like 180 degree. Remember, -1 in phasor form or in complex form, that corresponds to 180 degrees. Get, so you can see yeah, that's what you have here. So let's now calculate the gain, like the peak. So we'll measure the peak of this input. We already know the peak of this input, the amplitude, which is 1 milli, because it was specified in the, remember, in the sine wave I specified. But now the amplitude of this output, that's what we need to find out. So what I'm going to do is I would assume so to measure the amplitude of this, that's the difference between this point down here and let's say this point here, right? So so if this 0.26 and this 0.25, that means this 0.24, right? Then let's measure what this place is. So I'll just place the cursor here, place the cursor and press A, button A, and I have the value. So according to this, let me scroll up. The value says 0.2384. That's the value at this point. So what I'll just do it, so if you want to calculate the amplitude, it will be the difference between here and this point of reference I choose there. I just want to choose this point. I'm assuming that's where the, on the other side, that's where the wave start from. Okay, you can see it's almost that same point. So I'm choosing this point, 0.24 here. So it will be the final. So it's like, it's tangent now, right? It's just like tangent, the output, the difference in output over the difference in input. So difference in the height would be the final, which is according to here, this 0.2384 minus this start here. I'm choosing this to be the start, so that 0. Sorry, not 0.24, sorry, it's halfway between 2.6 and 2.5. So that's like that minus 0.2, should we call that that's 0.505, would that be right? Or 5.5, yeah, 5.5, yeah. Okay, so over the total amplitude of the input, you know the amplitude already is just 1 millivolts. So that's just 1 times 10 raised to the power of -3, and the answer I got here is I got 16 minus 16.6. So again, this very good. I think, what did we get again for the AC? For AC it was 18, right? 18. AC told us 18. Transient told us 16 16.6, and calculation predicted what, 16. So yeah, we're good. So we can say, yeah, right now we've designed a common source amplifier because specifications were well met. So we're good. So we can now move to the layout. Yeah, I think so. Let's just end the video here and see you next in the layout. Okay, yeah, bye for now.